I guess we are recording. Okay. Okay. We are recording. Um, Hello. Let's start our today's session. I'll just share my screen. Yeah. Okay. Uh, can you guys see the screen?
Yes, Raj.
Okay. Okay. Good enough. So hello all and welcome to the 10th live session for this course. Intro to Machine Learning. So today's agenda is I saw some questions being mentioned in the Google groups. So I thought we'll do those questions first, and then if time remains, we'll discuss a bit about graph neural networks, where the idea is you want to mix graph structure with the neural networks that we currently use, right? Okay, so we'll start with the first question. So I understand that the week 8 question 1 that we had, where we had a lot of, the whole big graph, and we had a couple of questions on the Bayesian network. So we'll do that a bit now, and then, go to the next questions. Um, um, Actually, let me just share my screen though. You might not be able to see the. Okay. Yeah. Okay. So yes. So yeah, we had a question like this, right? We have a Bayesian network. The first question of your week 8 assignment, and we're saying that all of them are binary in nature, and we're asking, which of these are following are true. So to answer these type of questions, there are multiple ways to do it. At least what I find a bit more grounded is the fact that we can use basic probability rules to actually come up with some solutions for this set of problems. Okay, so first things first, I want to confirm with you all, is this right or wrong? What do you think about this particular equation here? Why is it right? Why is it wrong? Any ideas? No ideas.
Hello.
Yeah.
So I just want to confirm you are summing over the indices, that is X, right?
Yes. Yeah.
So conditional on the Y, you are summing over all the possible results, right?
Correct.
Outcomes.
Hmm.
So that should be one, right?
Right. So this is actually just your conditional probability.
Yeah. Yeah,
So
I think correct.
yeah. So the idea here is, when you write P of X given Y, this is a probability distribution over which variable?
X.
Over X, right? But as a function of Y. Okay, so the random variable here, in some sense, is X, right? So and we know, like, the basic rules of rules of probability, that your uh, when you take over all the values of a random variable, the probability will sum to 1, right? Hence the idea here, that when you add up your all the probabilities for a given random variable, conditioned on any of the random variable, this will still be 1, right? um, Another way of looking at it is using this conditional probability sort of a thought process, where you say that P of X given Y is P of XY by P of Y, right? Now when I say summation over X P of X given Y, right, is basically summation over X P XY by PY, right? Now Py is basically independent of X, so I can pull this out, right? And I get summation X P XY, right? So this is the marginal of over x of the joint probability distribution of xy, right? So therefore this becomes just p of y, right? And therefore this summation is 1. Okay, so two ways of looking at it. So one is your basic probability sort of an idea, but in case you get ever confused like this, you can always reason out in this format, right? So so this summation has to be equal to 1 because it's a distribution over the random variable x, but it is a function of y. That's it. Okay. Okay. So this is one idea, and second thing that we saw, that when you have a joint probability distribution, for example, let's say a, b, c is your three random variables, and this p of abc is the joint probability distribution of these three random variables a, b, c. So when you add up over a, this is basically marginalizing over a, right? So what you get is the probability distribution of these two random variables, that is b and c. Okay, so using these very basic ideas of probability, we'll look at the second option here. Okay, p of ai is it equal to p of a into p of I for this particular Bayesian network. Okay, so so first thing is using the idea of marginalization, I can write this p of ai as the summation over all the remaining variables, right? That is b, c, d, e, f, g, h, and the probability distribution of the variables from a to I, right? A, b, c, d, e, f, g, h, I. Now I can factorize this into this format because of the fact that it's a Bayesian network, right? So this gives me what all conditional properties are enough to actually define the um, uh, joint probability distribution, right? So this comes out as p of a into p of b because a and b are at the root nodes here, right? And then you have your c given ab, e given b, right? So c given ab because c's parents are a and b, e parent parent is only b, f's parent is only e, g has two parents d and f, h has one parent f, and I has one parent h, right? So when you put it out like this, you basically get in this format. Now you can I can make this p of a outside of this summation, right? Because the summation is over all these variables where a is not a part of it, so I can write p of a outside, right? And now I am left with these variables summed over all of these quantities, these all probability the product of these probabilities. Now I can expand this summation, right? In this format I can say, okay, I will take summation over h first, f then, and so on, right? And now we'll look at this idea that this summation over g, p of g given df, this is similar to what you are looking at here, right? The first equation here. So this turns out to be just 1, right? So what ends up happening is your summation over d will have a summation over d p of d given c into 1, which is probability of d given c, right? And same thing again applies here because summation over d p of d given c, this is again 1. Again this is 1 because summation over c p of c given ab, this is also 1, right? Now if you see here, this is not clearly 1. So what we'll do here is, if you see, this is p of e given b into p of b, right? So what is this actually? I can write it as p of eb, right? P of eb, right? Now I'm saying, okay, so I will summate over b, but with this joint distribution. So this gives me the marginal distribution, which is p of, right? Now same thing I apply here. So I'll say p of f given e into p of e. This is basically my p of f comma fe, that is your joint of p of e and f. Then I'm doing a summating over e. So I get basically here this comes out to be p of f, right? Same thing I apply again here, right? So I get this is p of hf, summation over f, I get p of h. Again I apply the same logic here, I get p of I comma h, right? And then summation over h, I get p of I, right? So this is your p of ai equal to p of a into I. right? Now I understand that doing like this can take time. So hence we have those nice rules coming to picture where you say, okay, given this variable, what is which two are independent and so on, right? Actually we can prove those rules also using this sort of an idea, right? I mean, those rules were actually derived from this sort of an idea. So if you see here, in class we learned that when you have when you have something like this, let's say I, j and k. So given j, I and k are independent, right? So what does it mean? It means that if I were to write I k given j, I can write it as a product of these two conditions, that is I given j and into p of k given j, right? So that same thing we'll see here, whether it is true or not. For if I give c, are b and d independent or not, right? So that is p of bd given c. I want to see whether I can write it as a product of d given c and p given c probabilities, right? Now this is basically your probability of bdc given p of c. This is because of the idea of a condition probability, right? Now I put the same sort of a logic. I say p of what is p of bdc? It is the marginal over all these variables a to I except these three variables over the joint probability distribution, right? So I have summation a, e, f, g, h, I with of this joint probability distribution. So I can then put the equation again here and see basically that all of these variables will start summing out. So you will have summation over I. You will have p of I comma h, which gives me 1. Again p of h and p of h given f, you will get 1. P of g given df, you will get 1. And f given e, you will get 1. E and e given b, you will get 1, and so on. What entirely finally remains is this p of d given c is out in the summation. So I can take it out. So I'll have, and this p of b also is out of summation. So I'll at the end I'll have 1 by p of c. P of b is taken out of the summation. P of d given c is also out of the summation. Lastly, I have p of summation over a, p of a and p of c given ab, right? Now this is basically your probability of c given b, right? This is your probability of c given ab. So c given b. Now you can see here, this is probability. So probability of c given b into probability of b by probability of c, right? So from Bayes theorem, this is probability of b given c, right? So therefore I was able to write this probability, this joint probability distribution, which is conditional, as a product of the conditional distribution. So therefore I can say that b and d are independent given c. Okay, now in the same way, try to solve the first question here, that is p of ab given g. What will end up happening is you have the same form here. You'll say 1 by p of g, and you'll have like the summation over all these variables except a, b and g, and the same form. Now you can use this idea of summating out and basically removing out I and h here, because you'll have a summation of over I, p of I given h, which turns out to be 1. Same thing here, p of summation over h, p of h given f, which is 1. And so what ends up happening is you will not have a form where you can get something like this, p of a given g into p of b given g, right? So this is lost, right? So what are we saying here? We're saying that if you want to find this probability, you cannot express this as a product of these two terms here. So therefore these two are not conditionally independent. That is, a is not independent of b given g, right? Now so you can either use this sort of a method, or use this sort of an ideas where you keep on trying to apply this this sort of idea that, okay, given a particular node, which two nodes are independent and so on. I myself find that doing something like this gives you much more clarity and confidence in your process. Okay, so any doubts in this question, in this method of solving?
No, I understood the method.
Sorry?
Great.
Yeah, Somir, go on.
No, I understood the method.
Okay.
I will try with the third,
Yeah.
condition which was given in the question.
Right, yeah, yeah. Mm, this one is it? Yeah. So P of B given H, E given G. Yeah. So you can try it out and see, what is not clear here. You know? Okay. Good. So this is the this one. Yeah. So anybody else had a question?
Raj.
Yeah.
So, is this technique general enough to be applied to any graphs, any questions, any graphs?
Yes, right. So what are graphs doing here, right? So graphs are just telling you how can you factorize your joint probability distribution, right? Factorize the joint probability distribution. So if you have a graph structure and you want things like marginals, you want things like conditionals, since we can always express them as the ratio of two marginals, you can always use this sort of a method to find out what is the required conditional. Yeah.
Okay. Yeah.
Okay. Okay, good. Fine. So then we had this week 8. Question 3 was also asked. So question 2 we did last time. Question 3 we discussed, and I got this clarified from the your course TAs also. So mostly it it will be a grace question because the way the question has been asked is not exactly right. So I wanted to give you a brief idea of what the issue with the question is, so that you're able to appreciate exactly what PDF and CDF mean in terms of continuous random variables, right? So in case of continuous random variables, we define probabilities only over a range of values. Okay, now why this happens is because of some other mathematical technicalities. You have something called as Borel sigma algebra. Okay, this is not the right way of writing it. Yeah, Borel's sigma algebra, like this. Okay, so which defines things like on what things can you actually define a probability and so on, right? So when people try to write for this continuous random variables, these are defined only over a range of values. Okay, so for something like this, for example, let's say I have x, which is a continuous random variable, right? And okay, a single continuous random variable. We will not deal with multivariate right now. So what people said was that okay, so we'll define a probability in this format. I'll say, okay, the probability of a less than x less than or equal to b is some, let's say, something k. This k has to be between 0 and 1 compulsorily, right? Because the idea of probabilities is that it always has to be between 0 and 1, right? And this is one thing that they had. Second thing that they had was that so probability over the whole domain of x, right? So for example, let's say if x is defined over, let's say, 2 to 3 only. Okay, so if I were to write something like this: probability of 2 less than or equal to 3 x less than or equal to 3, this number has to be equal to 1. Okay, so with these rules and some more rules of this Borel's sigma algebra, we came to a thing that, okay, probabilities for continuous random variables, we will define probabilities only over a range of values. So hence, when you say p of x equal to a, right? So when you say, okay, what is the probability that the continuous random variable x takes one value a, this turns out to be we can write this as probability of a less than x less than or equal to a, right? Because the only value which lives in this sort of a range is that x equal to a, right? And this is then therefore defined as 0. Okay, so when you yeah, so when you okay, actually, let's just go forward and we'll come back to it. Yeah, so hence this idea that any continuous random variable, the probability of it taking a given value is just going to be 0, right? So we then define something called as the cumulative distribution function, that is called as CDF. So the CDF is a function which takes one value, that is x equal to a, and spits out a probability measure which is defined in this way, that is p of x less than or equal to a. Right? So if so the CDF of any random variable at a point a is basically the probability that the random variable will be less than or equal to the given value in question, that is a. Okay. And then we went ahead and found something called as a PDF. This is called as probability density function. Okay, so probability density function. So this density should remind you of many things here. So this is taken as a derivative of CDF, and that too, this is, if you want to be a math Nazi, you can write as this is for absolutely continuous variables, because continuity and all of that can have different meanings. So for special types of continuous random variables, yeah. So for some other reasons, we can have we may not have derivative existing, but we say okay, for absolutely continuous random variables, we say PDF exists, and that PDF is the derivative of your cumulative random distribution function. Now, when you say something is following a Gaussian distribution, what are you saying, right? The PDF of, let me write P of, let's say, x, okay, mu and sigma. This P is PDF of x. This is the random variable. These are the parameters of this PDF function. Okay, so these are the parameters of the function. This is a Gaussian distribution. Gaussian distribution has a proper functional form, right? So it says exponent of -1/2 sigma squared x minus mu the whole square, right? Okay, to be even more precise, I'll write it as capital X because that's the symbol we have used here. Okay, so this is the PDF of x for this given variables mu and sigma. Okay, so if you want a probability from this, what you need to ask the question should be like this. Okay, what is the probability that, let's say, x is between -1 and 2 and so on. And how you will do this is you will say, okay, I'll integrate from -1 to 2 because it's a continuous function. I will integrate this particular function, this function p of x mu sigma, right? And this actually just turns out to be, you can write it as the CDF at 2 for this function minus CDF at -1, right? Okay, so this is the idea. So hence this question, which was asking you that temperature equal to 66 and humidity equal to 90, is not the right way of asking this question. The way to ask is, okay, what is the if the temperature is between, let's say, some 65.5 to 66.5. Okay, so that's the gist of what I wanted to cover. For this question 3. Okay, so any doubts in this? Anything unclear?
Raj,
Yeah,
so you mentioned that probability at a particular point is 0, right?
correct.
So that is also referred to as that set is of measure 0, right?
The set is of measure 0, correct. Yes. Yeah. At least for this continuous random variables, you have non-zero measure only over a range of values.
Yes.
Yeah.
Your point is measured 0, right?
Point is measured 0, correct.
Okay. Yeah, fine.
Anything else? Okay. Yeah. So as I said, the question should have been something like this: what is the probability that, playing, is it not play? Yeah, student, let's say not play, or like P bar. Okay. Fine. P bar. Given your outlook is sunny, temperature is, for example, between 65.5 T less than 66.5, let's say, if you want something around 66, right? And then you say humidity 89.5 less than humidity less than 90.5, and the last one is again a discrete variable, so when d is equal to true or whatever, right? This you will solve it using the thing that we discussed last time, right? Using the idea of your I think this is a naive based, yeah, so naive based method, and you will try to see, you know, how to I mean, you will say that okay, it is all these features are independent given the class, and then you will apply the Bayes theorem to get your probabilities. Okay, fine. So this is the this is that question, week 8 question 3. Then we had this idea of so week 8 question 4 is something to do with this gradient boosting and ADA boost. Again, I'm not very clean on these methods. I've never studied or even used them. The way I understand is that it is some exponential weightage versus squared weightage, right? For your values of your function output. So they're asking which is more sensitive to outliers. So very simply, from this, the idea is that whenever you have an outlier, the weightage of your of that particular point in your loss, right? So how much it contributes to your loss will be higher for first of all exponential, then you have squared, I mean squared, and then you can like absolute difference, right? Absolute difference sort of a thing. So hence in this case, on these lines also, we generally say that MAE as such, your mean absolute error, that is less sensitive to outliers compared to MSE, right? Because MSE, what MSE does is it says look at the squared error, right? Look at the squared error, right? And so let's say if your prediction was, for example, let's say 10, and the point was an outlier, I mean, so it's a prediction and this is the target, was for example, let's say 90, the difference is actually just 80, but your square error will say 80 squared, and your MA will just say 80 as your loss, right? So compared to other values, this will get like a very high weightage, and therefore MSC will try to solve for your outliers. Like I mean, it'll get heavily biased because of these outliers, and hence like from there it'll like you have this outlier removal sort of thing makes a big, you know, impact in many of the ML algorithms. Yeah. Okay.
That's sorry to interrupt you.
Yeah.
So here in the gradient boosting, the
Okay.
loss function could be anything. That's what sir said in the lecture. So for for Adabut, it is confined that it should be exponential loss function. But for gradient boosting, there could be any loss function. But sir explained using the least square function. But it could be any loss function. So considering that, wouldn't gradient boosting also be
Similar or more than this? I got your point, but I think what they meant is that the naive version, the most basic version, I think uses the square sort of approach, if I'm not wrong, MSA sort of a thing. Yeah. So I actually saw this in when I was going through these methods. The gradient boosting can use any loss function as such. I think we can use even your usual MAE also, for example. But I think the naive version, in some sense, is what is, you know, asked for. That should have been, I mean, clear from the
that should have been mentioned, right?
Yeah.
So
okay.
Yeah, and one more point, Raj.
Yeah.
I think I second Somil's point, because boosting is a meta algorithm, right? So it can apply any algorithm as its objective function.
Right.
And boosting is also higher performing also. So in that sense, it makes a much more sense that that would be more less prone to outliers than the re-squares objective. I'm not sure. This question is kind of very confusing.
Okay. Okay. So I'll ask them. Let's see. We'll see. I'm not sure exactly. How much this would be a strong point. But see, I see when you say linear regression, you can also do a regression using your MAE loss, right? If I'm not wrong, right? Because you can always say, okay, I will not look at y minus f of x squared as my objective. I'll look at y minus f of x as the absolute value of this, right? But when you say in a regression, you generally mean the MSE loss only. So I think in that sense is what sir meant, that gradient boosting, when you say just usual gradient boosting, it just means your squared error sort of an approach. So we'll see, I'll talk to the course TAs if there is a if we can change that in some sense.
Okay, thank you.
Yeah. Okay. Okay. Good enough. So that's the question 4 of week 8. Yeah. Yeah. Okay. Then we have this idea of, week 9, question 3. So the idea, week 9, question 3 was, yeah, that, okay, one second. I'll just open it here. Yeah. Week 9, question 3. Yeah, this one, right? Okay. So we're asking that, how many turns will be there in the potential function factorization. So, the idea is that you want to find the maximum cliques of the graph. Now, there is no standard clique finding algorithm as such. So it's NP hard in some sense, because you need to check every possible edge, whether it belongs to this clique and so on. But then, so what you could do is some sort of a degree based idea. So I'll give an example of how I would go about solving it. So for example, if you see here, this node E has two edges with it, right? So if I can form so the maximum clique size that this node E can be or can belong to will be of size 3. 3 nodes forming a clique. So I might be able to subsume both of these nodes, both these edges in that. So then, if you see here, I can form this EAD as one clique, and similarly, I can see here BFC as one clique, and then so once you have done with that, you can basically see that, okay, without considering these two nodes, can I look at something else? In this whole graph. So from a visual sense, you can see that, okay, it's A, B, C, D have is basically your K2 graph, right? Sorry, K4 graph. You have all the possible edges, so it's also a clique, and therefore I have 3 cliques here, which is the number of terms in the potential function, right? So is this what you expected to to solve for this question, or you want something more from this for this question?
Raj, so my question was that for a node, if you consider, so there
Yeah.
will be 4 cliques, right? So A to E, A to D, A to B, and A to C. Like the whole 4 edges would be considered for the clique, for a single clique, right? Like
No.
we want A and F should be independent. Means there shouldn't be a single clique between A and F, and all other nodes which are directly connected come under a single clique, right?
No. See, okay, I think that's some confusion, I guess. One second, let me just tell you what I think of this. Okay, so clique is basically some a subgraph of your graph, right? It's a subgraph which is complete, right? So complete in the sense, when you say K4, for example, so we represent complete graphs by the notation K, and the number of nodes in the graph as, let's say, with this subscript 4 here. So K4 would be something like this, right? So because I have all the possible edges between all possible nodes, that is your 4 nodes here. So I have these 4 nodes, connecting them in a rectangular format, and I also have these two edges here. So what I'm saying now is, let's say I have this, right? So like this. So so the idea is that you want to see, let's say this node E, right? What is the maximum this maximal clique that it can belong to? Okay, so maximal clique in the sense, every node by itself is also a clique, right? Because I can say this is K0, right? Sorry, I mean K1, sorry, K1, right? Because I can say, okay, this is a single node, so there's no more edges to have, so it's a complete graph in its own right. I can also say E, and for example, I think this was D, is it? Just let me, yeah, D, right? So ED is also a clique in itself, because I mean it's a subgraph which is complete, which is K2, right? Or I can also then look at E, A, and D, right, which is basically K3. Yeah, K3, right? So the question is, okay, so I can do all of these. What is the maximal in these three? These are maximum, right? So for E, there's one single maximum that we found, right? One possibility that we found. So I basically say, okay, this is one, a clique, maximal clique that I have found. I cannot increase like I cannot include this E into any other clique such that it its maximum it has more nodes than K3, right? Similar idea comes from here. So these three become another clique. Now the thing is, as you said, like this A, I mean A has 1, 2, 3, 4 edges here. Now this edge is already in some way subsumed, or basically being covered by this clique, right? But the question is not that. The question is, can I find something more for this A, right? More than this, for example, this clique, for example, which covers this A in a best possible format, right? So and the answer is yes, because I can find a K4 node, a K4 subgraph, which is of these, right, A, B, C, D, right, which is having which is a maximal clique for all of these A, B, C, and D, right? So this becomes another a factor in your potential function, right? So it's the way to find your cliques and your factors of your potential function. Okay, so any so was this unclear, or what you understood was it fixed? Any feedback you have?
Yeah, so I don't understand why would E won't come in the clique, like A, B, C, D, and E, if you consider as a whole cycle.
Okay.
So
Okay, I got your point. Okay, so A, B, C, D, E, when you choose, that means it has to be a complete graph of 5 nodes, correct?
yeah, yeah.
Okay, so if I do that, I mean, sorry, let me, yeah, let's say node 1, node 2, node 3, node 4, and node 5, right? So what all should come here is 1, 2, 3, 4, 1, 2. These edges should also be part of this, right? So I should have basically 5 into 4 by 2 is 10 edges I should have. So 1, 2, 3, 4, 5, correct, yeah. So here if you see, E and B are not connected, right?
Okay, got it, yeah.
So hence, yeah, so hence the maximum clique that E can belong to is just 3, and therefore
so every node has to be connected to every other node for becoming the clique.
Correct.
Right?
Yeah. So this complete is the keyword here, right? So basically your this particular K3 is complete because every possible edge is a part of this EAD graph, E subgraph. Yeah.
Okay, got it. Thank you.
Yeah. Okay. Right. So that's the question 3. Question 4, week 9. I actually had a brain teaser for you guys. So I think there is we know that for HMM we should have your one element only. I mean, sorry, it should belong to just only your immediate past should affect your current present. So but we know that in Fibonacci sequence, what ends up happening is, for example, let's say 0 and 1 are your first two Fibonacci numbers. Again, this is contested, but let's just move ahead with that idea. So the third number comes from these two, that is 0 and 1, and the next number comes from these two, right? And then again the next number 2 plus 1, right? So that comes from here, and then 5 comes from these two, and so on, right? So as we see, like we actually have a dependence on 2 past steps, right? So if you're done a basic computer science course, you when they teach recursion, the first thing that they teach is this sort of one of the first things that they teach is how will you calculate Fibonacci sequence using recursion and so on. Now my question to you is, can I construct a Fibonacci sequence using a one dependence only, right? So construct Fibonacci sequence using a Markov assumption. Okay, so how would you, if you had to do this, okay, so how would you go about, doing something like this? Any ideas?
Can we, I'm just putting out some ideas. So can you just try to solve the recursion itself and see that whether we can eliminate the dependence on the penultimate last to the previous term and see somehow, means I'm just thinking out something.
Yeah, but how will you, yeah, how will you do
Yeah.
that?
This also stumped me actually as a question. So,
yeah, so if I say that, construct a sequence in some sense that uses only the previous state and not the or not the future states, and I will say that, okay, I can solve Fibonacci sequence using this sort of an assumption, using a Markov assumption. How would you go about doing it? Okay, so what we'll do is, we'll construct something like this. Let's say this is my state, okay, uh, I, and I will use two elements in my state. Okay, that is, let's say initially I will say 0 1, okay, and the next state I'll define in this format. I'll say, okay, whatever was there in the below, that is, I will use it here, okay, and this sum I will use it here. Okay, and I will output.
You will be converting it to a two first order equation sort of thing, right?
Correct. That's it.
Got it.
Yeah, yeah. So what happens is, okay. So I'll complete what I was saying. So let's say this is A and B. Okay. So you have your A and B at time t here. A at time t plus 1, B at time t plus 1. Let's say two elements here. Okay. So what I will say, okay, A t plus 1 is BT. BT plus 1 is AT plus BT. Okay, this is my hidden state. Let's say this is my hidden state movement, and my output, okay, my output, that is OT, for example, is always BT. Okay, so what I will do, output is 1 here, the output is again 1, right? And then I will say, okay, form my next state, which is basically copy this 1 here, add these two, and output is 2. Same thing I will do here. I'll say 2 and then add these to 3, output 3, and then take 3 here and add these to 5, output 5, and so on, right? So what you got output was a Fibonacci sequence, right? So this idea of using this a more complicated state, because here what we are assuming we have a very simpler state, we just have numbers as my state. So what I'm doing here is I'm actually trading off the most basic trade-off that we can ever have, that is space versus time, right? So what Markov tells you is that I will not I don't want to maintain multiple time steps, right? But Fibonacci sequence tells you either maintain multiple time steps, right? And when you put this constraint that I don't want multiple time, what you will do is you'll actually just subsume whatever your previous states were into your current state, hence increasing the space, the amount of data that you need to store at every time point. Okay, so this idea of solving a finite so see, the idea here is that your Fibonacci sequence which you had is actually a finite past dependence sort of an issue, right? Your current time depends on finite past, given finite past, right? So if I know t minus 2 and t minus 1, I can find out t easily. I mean, in some sense, right? So therefore, so all of these finite past dependence problems can actually be subsumed under this Markov assumption by taking all the states into this. So it's the biggest power of this Markov models, right? So you might think that the Markov assumption is very sort of very like free in some sense, like we're just saying okay, depend only on the previous time point, but it's not true. You can always increase your state representation to actually form a Markov chain, and then basically apply all those nice properties which we have on Markov chains. Okay, so so this is the idea that you can construct a Fibonacci sequence using a Markov assumption. Okay, but yeah, the answer, I mean, here is not taken to be a Fibonacci sequence, which makes sense because the idea is that you have a when you take time as your or basically steps as your steps in your HMM, it actually depends on two past steps. But if you had to construct something like this, you could do it in this format. Okay, fine. So this is the
Raj,
question.
this we can also consider as a Markov chain, right? Because the state may be vectors instead of scalars. What is the difference? Means I am not getting this point.
Which point?
Yeah, so see, you have constructed, the way you have constructed, written down a sequence of numbers for every hidden step.
Correct.
So that can also be regarded as a Markov chain in itself, right? Because
Correct.
Because the output depends only on the hidden state only, and the hidden state depends only on the past state.
Right.
But in the question, it's not considered as a Markov chain. Why?
So it's not considered because the way I think they have they intend this question is that you want they wanted to see that okay, I know something like this cannot be trivially constructed into a Markov chain. You need to do something extra to your state to be taken into this one. But in case I mean if you feel that okay, this is not a right way of looking at it, I can talk to you. I can talk to the course TAs, but yeah, we will have to see. I'm not sure if that's.
I selected it as the correct option. That's a Fibonacci sequence, but they have made me incorrect.
Okay. Okay, fine. We'll see. So actually, okay. So in that sense, what about this trajectory of baseball, by the way?
Yeah, that is also kind of same thing, right? You integrate over the past.
Correct.
You have the current state as well as the velocity as a Markov hidden state, right?
Right. Exactly. Henna. So because when you use, for example, let's say without friction and all of that sort of thing.
Yes.
The idea here is that you have something. You have a force acting on your ball. So therefore you have the trajectory, that is your basically your position, let's say x, depends not just on the velocity, let's say dx by dt, but also on the your acceleration, right? So therefore so the way to look at this acceleration in terms of discretized time points is that you actually want to look at two past steps, right? So for example, let's say this is the x2, x1 and x0. So to find the acceleration at this point, what you look at is, you will say I will see the difference between x2 and x1. This gives me the velocity here, this gives me the velocity here, and I will look at these two differences to understand what is the rate at which my velocity is changing, which is basically your acceleration. So therefore the idea is that if you want to move from x2 to x3, that is, you want to predict the trajectory of the ball, you need access to x0 and x1, and hence it's not trivially a hidden Markov model because you have two time dependence. But in the same way, you can actually form your state to be something like this. You can say it is either I can keep x1 x0 x1 x0 x1 x2, right? I can use all of these, or I can just keep my the velocities in place. For example, let's say this let's say I'll call this v1 and v2. I'll keep v1, v2 and x2 and so on. Again, we can test all of these ideas in some sense. So, but the idea is that the next state now will just depend upon these three values. That is, your x1, x2, x3 will be your new state. And the thing is, this is your hidden state. The output of this particular HMM will just be your x2 and x3 and so on, right? Which is the predicted trajectory of your so and so of the baseball. Right, so we can apply this idea here also. So okay, let me talk to them. Yeah, we'll see. I mean, I'm not sure this is what they intended. All right, yeah. Any other questions regarding this question of hidden Markov model? No. Okay. So we'll go to question 6 of week 9 was also asked. Yeah. Oh, yeah. This is your optimal what is it called? Optimal variable elimination sort of a question. So we had the question was that we have a graph like this. We have a graph like this, and we want to find what is the probability of E. So in this case, what would be the the right way to eliminate the variables? So you can actually again use the same idea. You'll have your summation over P of A, B, C, D, E over all these variables, and you can write it out as the product of these conditional distributions from your from the graph representation, and which can then be simplified into in this sort of a format, right? I can say summation over D, then C, then B, then A. So the elimination order, that is which is the variable which gets eliminated first, is A, right? Because you will come from left to right when you're trying to solve this summation. So hence the order in which it gets eliminated is A, B, C, D. So hence A, B, C, D is right. Okay, so I'm not sure what the question here was, but in case you're getting confused, for example, because I can always write the summation in this format also, right? I can write as A, B, C, D here, but it is not optimal because here you have to deal with three variables, right? You deal with D, C, and E. Three variables you have to deal with here. Here it's two variables, and once you solve this summation, you'll actually just have P of B here, and then you have P of B and P of C can be again two variables, and so on. So you always have like a very small table of two variables coming into picture, right? Here you'll have like three variables, and basically until the end I think you keep on having three or two variables, and finally it gets solved as your you'll get your P of E, right? So the optimal is in this format, and which is so the elimination order happens A B C D, A B C, A B C D. Okay. Okay, so this is the solution. Any doubts here? Anything extra you want from this question? No. Okay. Yeah. So I thought somebody also had the question on the naive Bayes assumption. Was it? Oh, that's week 8, is it? Okay. So week 8. So see, the what is the naive Bayes assumption telling you? It tells you that your features are independent given the class, right? That is, for example, let's say we have two features and two classes also here. So what I was saying, I'm saying that feature 1, feature 2 given the class is, let's say, 0, should be equal to P of feature 1 given 0 into P of feature 2 given 0, and for 1 also, right? So I can just write it as some the classes that we have in question. Okay, so see, if you don't use a class information here, these two features don't seem independent. Okay, and which is sort of obvious, right? Why? Because what's happening here is whenever feature 1 increases, right, I can see that I have a higher value for feature 2 also, right? So there's sort of like a positive sort of a relationship happening here. It's some sense of in some sense it's a positive correlation that's taking place, right? So these two don't seem independent, but given the class, if you see, so given 1, for example, you have a bunch of values for this feature 1, feature 2, and I can find like values for feature 2 which are smaller and more compared to this feature 1 increment or decrement, right? So if you see only the blue cloud here, so as the feature 1 increases, for example, when I'm going from left to right, I see values on both the sides of this. I see values of feature 2 which are lower and also higher, right? So it doesn't seem like the features are correlated, are dependent when it comes to class the conditional sort of probabilities. So hence we say that given the class, the features seem to be independent, and therefore we say for this question that neighbor assumption seems to be holding, right? Okay. Okay, so the point of this exercise was to give you like a more pictorial way of looking at this independent sort of an idea given class sort of a thing. a more better way to treat this sort of an issue is basically actually looking at different measures of independence and so on. That is not expected here. The idea is just that does it seem to be independent or not. That's the idea of this question. So here we say that it holds, this assumption holds for this particular sort of a data set. Okay, any questions here? No? Okay, so we'll move to the we just have like 2 minutes, but okay. So the idea that you want to learn, for example, let's say graph structures. Okay, so in like we have many ways to do this. One way of using neural networks with graphs is basically having something called as a graph neural network, right? Graph NNs is called. The idea is that you want to learn some feature mapping between the input to output with the thing that I have a graph structure on the input feature space, right? So we have to give something to the neural network to tell that this is the graph and treat this a bit specially, right? So we basically give something called as the adjacency matrix, right? Because one way to represent any graph in a structured format is by using this idea of adjacency matrix, where you list down all the nodes, let's say n nodes. So you have an n cross n matrix, and it tells you a varied amount of information from just whether two nodes are connected, right, to do we have positive or negative weights and so on, right? So we can have like a many different things from this particular matrix to extract from, and we hope that the network will actually use information to learn something about this input feature space in some special way, and use that to predict your output a bit better. Okay, so I had a couple of things here, so I'd say just go through it in case you're interested. So one idea I want to give you in terms of the domain that I work in, that is the brain data. So assume that this is a brain. Okay, we have a front of the brain and back of the whatever. So when you do a fMRI sort of a study, that is you're getting some signals from the brain. So you basically have like one value per region. So now what you can do is you can either treat it as a 3D image, right? So basically treat it as like some volume sort of thing, right? So take it as, for example, let's say some volume, and basically each of these elements here has some value in it, right? So treat it as a 3D image and use like a CNN sort of an approach to solve it. Or what you could do is you could basically model the brain as a graph and say that, okay, for example, this is the the PFC sort of a thing, which is a prefrontal cortex is one node of my graph. I have, for example, the V1, which is a visual cortex, which in the back of the brain is one node of the graph, and basically assign values for these particular nodes, and then try to learn how these regions are interacting with each other to produce some phenomena. Okay, so this is the idea of using graphs in this domain of neurosystems. And we also have something called as time varying graphs, right? So for example, the graph itself can vary from time to time. So can you think of a simple example of a daily life where this can be used to model your system? Any ideas? A very trivial daily life thing which people go through and can be modeled as a time varying graph. So your traffic systems, right? So your traffic basically in your city or in across cities or across states, across countries and so on, can be seen as a graph, right? Where your nodes can be, for example, some hubs of your city, for example, right? So main has, for example, if you're in Bangalore, in case you're in Bangalore, you would have heard about something like Silk Board or whatever, right? So you have Silk Board, you have Majestic, and so on, right? You model these as your nodes of your graph, and basically the amount of vehicles here, moving from one node to the other node as some value which is varying across time, right? So in this sense, we also have a time varying graph sort of an architecture which is used, and this with neural networks, we have things like graph RNNs and graph LSTMs, which have come up a bit recently in the domain. Yeah. Okay, so this is about graph data sets. I think next session we'll have it on unsupervised learning. Any doubts right now? Else we'll close the session. Yeah.
No doubts, Raj. Thank you for this.
Okay. Okay. Good. So we'll meet next Saturday on this one, unsupervised clustering sort of algorithms. Okay.
Raj,
Yeah. Swami, go ahead.
yeah, so can you suggest some references on fMRI in the context of graph modeling, so that I'm a little bit interested in that?
fMRI into the graph modeling, is it? Okay, yeah. So I'll put it in the PDF when I send it out. You can have a look.
Yeah, please. Thank you. That will help a lot. Yeah, thanks.
Okay, guys. Okay, see you on next Saturday.
Yeah, thank you.